This presentation will talk about calorimetry. We will describe what calorimetry is, we will define system and surroundings, and we'll relate the math to conservation of energy. Finally, we'll solve some problems about various types of calorimeters, including the coffee cup calorimeter and the bomb calorimeter. So what is calorimetry? Calorimetry, as a word, is derived from the Greek words calor and metris, which mean heat and measure, respectively. So calorimetry is literally heat measure. We're measuring heat, the way that it moves in a system. So the device we use for this is called a calorimeter. The two calorimeters given in the book are the coffee cup calorimeter on the left-hand side here, and the bomb calorimeter on the right-hand side. The coffee cup calorimeter has that name because it's literally two nested coffee cups. Very highly scientific instrument we're using there. Very affordable, and it does work. Thus, you will have a lab using a coffee cup calorimeter. Now, the bomb calorimeter, which is used for combustion reactions, is called a bomb calorimeter because it can, in fact, explode if you do the things wrong. So in order to make sure that combustion goes to completion, you put an overpressure of oxygen gas. You put a lot of oxygen gas in there, and then you spark it. And that reaction happens really fast. And if you haven't properly sealed the container, kaboom. Oops. Generally with lots of water, but that's a different story. So these instruments are about a 1/2 inch thick steel, just to burn 1 gram of material. Kind of put that in perspective. Anyway, either case, when you're using a coffee cup calorimeter or a bomb calorimeter, we are going to use similar mathematics. Both of them try to be thermally insulated so that you can't let heat out to the surrounding area. And we're going to observe changes in the temperature of the water used in them using the Q equals mCAT equation to solve for the energy, or the heat rather, of whatever change we're observing in the system. So let's talk about the theory of why that works, and then we'll try to do some problems and demonstrate how that works. So in thermodynamics, we can define anything as the system, anything we choose, and everything else that we don't choose as the system is part of the surroundings. So if you're talking about studying the amount of heat your house loses to the air, you might get a thermal image taken, just like this. If we want to know about how much energy the apartment building is losing in this picture, what is the system and what is the surroundings? So the system would be the apartment building, and the surroundings is literally everything else in the entire universe. All of it. Every last thing. Once we've established this fundamental relationship, this definition, we can move on to how we observe these changes. So generally, for a calorimeter, we refer to the system as the chemical that we are studying. So in a coffee cup calorimeter, that would be either a metal that you dropped in there, or it will be the water that is the solution that you're doing the chemistry in. In a bomb calorimeter, it's the sample and the oxygen, and everything else is surroundings. We try to make sure that we insulate our calorimeters so that the heat transfer is not happening to the wider universe. In a bomb calorimeter, there's generally a little bit of a vacuum that goes on that prevents heat from transferring, and it's the foam if you're talking about the coffee cup calorimeter. This brings us to the law of conservation of energy, which is sometimes called the first law of thermodynamics. There are different iterations of this law depending on the application that you're using. The one that we're going to use for calorimetry is as follows. Energy cannot be created or destroyed during a physical or chemical change, but it can change form. So Q system, Q being heat, plus Q surroundings is equal to 0. Meaning nothing changed overall. So why am I mentioning physical and chemical changes? Turns out there's a relationship between energy and mass given by nuclear reactions. You might be familiar with this particular equation. It's E equals mc squared. Yeah, that's right. Energy and mass, you can convert between the two if you're doing a nuclear reaction. But that's not what we're doing. By changing form, that second part that's a little bit sketchy, I'm referring things like energy can be transformed from chemical to electrical. So how do we do that? Well, we can generate electricity from batteries using chemical reactions. We do that a lot. Energy can be transformed from potential kinetic. So we're talking about balls rolling down hills. They had potential energy when they were at the top, but by the time they get to the bottom, all of that potential energy has been converted to kinetic energy. Another way to do that would be discharging a capacitor. And the last point, what you lose from one part of the system will be transferred elsewhere with equal magnitude and opposite sign. Q cis is equal to negative Q surroundings. So this is actually a restatement of our original law, where all I did was subtract Q surroundings from both sides. That's the math that we're actually going to use when we apply it to calorimeters. We're going to start with an example involving the coffee cup calorimeter. And the scenario runs like this. You drop a piece of hot metal into water in a calorimeter, right? Because the coffee cups are nested and you've got water in there. And you measure the temperature change using a thermometer. Now, we know from the previous slide that the energy or the heat that the water gains will be given up by the metal. And we know that we can measure what's going on using Q equals mCat. So Q is heat, M is mass, C is heat capacity, and delta T is the change in temperature. There may also be times when you're looking for mass. So mass and heat capacity tend to be the thing you're looking for. Delta T is usually what you measure with the calorimeter to begin with. So let's read our problem here. If 15.0 grams of unknown metal at 43.4 degrees Celsius cools to 25.33 degrees Celsius in 25 grams of water that started at 25 degrees Celsius, what is the heat capacity of the unknown? Now, I just threw a lot of information at you, but let's try to break it down a little bit so that it's not super intimidating. The first thing we need to know is what our energy differences are. So for our metal, make the metal red because it started out hot. It went from 43.4 down to 25.33. And for our water, we'll make that blue because water's usually blue. We went from 25 to 25.33. So this is the initial temperature. Okay, and I'm using a funky eye because I mistake my eyes for other things if I do it otherwise. And this is TF for both of them. Okay, and then I have 25 grams of water. That corresponds obviously to water, and then we also have the 15 grams of metal. All right, so now that I've collected all of my variables, I'm going to go ahead and plug them into the Q equals mCat equation. And I'm saying Q of water is equal to Q of metal. So I have all the information from water on the left-hand side, and then I have the negative of the metal information on the right-hand side. So 25 grams of water, the heat capacity of water is 4.184 joules per gram degree Celsius. And then I have my temperature change. I'm going from 25.33 down to 25. So that's my Q equals mCat. And I set that equal to the negative of the Q for the metal. So that's 15 grams of metal times the heat capacity of the metal times the final temperature, 25.33, minus the initial temperature, 43.4. Now, 25 minus 43 is going to give us a negative number, but a negative of a negative is, you guessed it, a positive. So when you plug these suckers in, you're going to have a tendency to accidentally put the temperature in the wrong place. It's always final minus initial. If you put it in the wrong place, then you will get a positive number equal to a negative number, which is not a thing. If you forget the negative for your Q water equals negative Q metal, you will also get the wrong sign, even if you put the temperature in correctly. And if you do both of those things wrong, it'll look like you did it right because you get Q positive equals Q positive, but oops, not necessarily the case. So I'm going to say it right now. Be very careful to identify final temperature and initial temperature for both things that you're measuring when you do these problems. Okay, now that my little PSA on be careful with your variables is over, go ahead and solve for C of the metal. So that's just a little bit of algebra. I'm going to assume that you know how to do that. And I get 0.13 joules per gram degrees Celsius. You should not get a negative C value, nor should you get negative mass. Again, this is how you will know you have done things wrong, either in the order of your temperature difference or in forgetting the negative sign on one side. All right, so now that we have assessed how to figure out heat capacity for a coffee cup calorimeter, let's try a different problem. A sample of copper was heated to 120 degrees Celsius, then thrust into 200 grams of water at 25 degrees Celsius. The temperature of the mixture became 26.5 degrees Celsius. And the specific heat of copper is 0.385 joules per gram degree Celsius. What is the mass in grams of the copper sample? Okay, so instead of solving for our heat capacity, we've got the heat capacity, and we're looking for mass. All right, so in this case, Q water is equal to Q metal, and the metal is copper. We know that from the law of conservation of energy. So each material is experiencing a temperature change without a phase change, and therefore Q equals mCat for both water and for copper. So let's track our stuff here. Our copper starts at 120. That's our TI, and it ends up at 26.5. That is our low temp. The water starts at 25, and it also ends up at 26.5. So it reaches thermal equilibrium. All right, we additionally have the heat capacity of the copper, and we want to know the mass in grams of the copper. All right, so we've collected all of our information. We know the heat capacity of water because, again, 4.184 joules per gram degree Celsius. And so we just go ahead and we plug things in. And also, we have mass of water. All right. So we put all of that in there. And we know that Q of water is equal to negative Q of copper. That was part of our definition, right? And so then we take that and we set that equal to that Q is equal to the mCat for copper. And so we isolate the variable m. And when we do that, we get 35 grams of copper. So basically, we just need to make sure we keep track of our variables, and then we can just plug and chug, right? We're doing algebra. Algebra is not too bad. All right, so let's try a different thing. Let's try to find a heat of reaction. How is this different? Well, in this case, we are measuring the temperature of the water, and the water has our ions in it, and that's what's reacting. So we're trying to look at, if we mix two liquids together, how much heat is evolved. Now there are, in fact, calorimeters that are way better than the coffee cup calorimeter that are meant specifically for solution chemistry. Way more sophisticated, automated in some cases, but they're not nearly as affordable as, 10 cents for coffee cups as opposed to like $3,000 for your relatively beginning of the line system. I digress. Okay, so it's going to follow the same mathematics in general, but we have to change a couple things. So we know that the overall energy of the system will not change. In this case, we're mixing an acid and a base. So if we have the energy from the acid, the energy from the base, and then the energy from the reaction, all of that together will mean no change in energy. Okay, so I'm putting A for acid, B for base, and RxN for reaction. All of that together, no change in energy. That's how we follow the law of conservation of mass here. Okay, we mix these things, we track the temperature. So in this case, you mix 100 milliliters of water with 1.0 molar HCl with 50 milliliters of 2.0 molar NaOH. The temperature of your solutions starts at 25 degrees Celsius and heats to 34.2 degrees Celsius. What is the heat of reaction in kilojoules per mole? And that's a standard thing that heat of reaction would be in kilojoules per mole. So how are we going to figure this out? We need Q of reaction. So Q of reaction, if we isolate that variable, is going to be equal to Q of A and Q sub B added together. So I can add QA and QB together. I just plug in the variables, right? So I've got 100 grams. I have a heat capacity of dilute ions in water of 4.05. I'm multiplying that by 34 minus 25. I'm adding it to the base component, 50 times 4.05 times that same temperature change. And that gives me negative Q of reaction. All right, so when I plug this through on my calculator, I get 5,600. And if you're looking at that and going, why does it only have 2 sig figs? If you do the subtraction, 34.2 minus 25 gives you 9.2 degrees Celsius, which has, yeah, you guessed it, 2 sig figs. So when you're doing this type of calorimetry problem, base your sig figs on your delta T. Moving on. So I found negative 5,600 joules of energy for this reaction. But that does not bring us to the end of the line, does it? It does not. So we're going to take that and convert it to kilojoules first, because that's pretty easy to do. We know that there's 1,000 joules in a kilojoule. And so we find that that reaction generated negative 5.6 kilojoules of heat. But we need to get it per mole. So how many moles of stuff did we generate? Because that's what our heat of reaction is going to be related to. We need to find our limiting reactant. So if you take the molarity and multiply it by the volume in liters, we will find the number of moles of stuff that reacted. And in this case, it's always 0.1 for both HCl and NaOH. So we don't really have a limiting reactant or an excess reactant. We just have product we make. Okay, so now we're going to divide our negative 5.6 kilojoules by 0.1, and we get negative 56 kilojoules per mole. Not too bad. Pretty close to the actual number, which is like negative 55.83. But just involves an extra little step here, right? Q of reaction. You're going to do this in lab. It's going to be tedious. You're going to literally watch the temperature of water change. But you will get cool stuff. Okay, moving on. We're going to do some bomb calorimetry. A bomb calorimeter with a heat capacity of 10.7 kilojoules per degree Celsius is used to burn 1 gram of fuel with a molar mass of 180 grams per mole. The water in the reservoir has a 1.46 degrees Celsius temperature rise. What is the heat of combustion of that fuel in kilojoules per mole? So in this case, Q of the calorimeter is equal to negative Q of combustion. And I call it a heat of combustion just because I'm combusting something. I'm burning it up, right? So this is how much energy that combustion reaction would release. Now, in the statement of the problem, there is something that is a little bit odd. The heat capacity of my calorimeter is in kilojoules per degree Celsius, and we are used to seeing heat capacity as joules per gram degree Celsius. So it's different on two counts. We're using kilojoules and we're not using grams at all. Why do we do that? The actual mass of the calorimeter, the calorimeter itself, does not change from run to run. It's exactly the same. So we're just going to roll that in as part of the constant in order to simplify our math. All right, and why are we using kilojoules? Turns out most of the changes that we're going to be observing are in the kilojoule range, so it's just easier. Okay, so let's start plugging in our values. We know that Q of the calorimeter is now equal to C delta T, and that it's equal to negative Q of combustion. So we put in our C of the calorimeter, we multiply it by our temperature change, which is positive because it rose, and that's equal to 15.6 kilojoules. We can calculate the number of moles of stuff that we used, so that's 1 gram divided by 180 grams per mole, and that gives us 5.56 times 10 to the negative third moles of fuel. And then when we divide our heat of combustion by the number of moles, we get negative 2.89 times 10 to the third kilojoules per mole. Okay, now if you read the example of bomb calorimetry from the book, they give you an amount that the water changed temperature, and they also give you the heat capacity of the calorimeter. They just added more steps. Active has both, and I wanted you to see both so that it wasn't a surprise. So please read your book for the other type of example, and hopefully the logic will make complete sense because we've been talking about the same thing, energy being conserved, in all of these examples. So to summarize, the law of conservation says that energy cannot be created or destroyed, so Q system is equal to negative Q surroundings. The system is what we're studying, and everything else in the entire universe is the surroundings. Calorimetry problems always involve the heat from one process being absorbed by something else and being measured as temperature. So we always use Q equals MCAT.